All right, hi physics people. So just like we talked about series circuits with resistors, let's talk about parallel circuits with resistors. So this means this type of setup where we've got a battery. It's connected to a resistor. And then instead of being along the same path, we have a branch in the path and another resistor connected like that. We could draw this diagram in different ways, different orientations, but the idea is that to get from the positive to the negative side of the battery, the current could go through either the first resistor or the second resistor. So if we want to look at this set up on a breadboard, the simplest way to set it up would be like this. The positive side of the battery and the negative side of the battery are plugged into different rows here on the breadboard. And then to get from this row to this row, the current could either go through this resistor or through this resistor. So some of the current is going to go through one, and some of it is going to go through the other. So I'll leave that there for a minute. And now let's talk about what this would look like in our air demo. So hopefully you remember we had a box. The box had some air in it in a bag, and the air was being let out through a straw. So with it like this, there's only one path for the air to get out of the box. If it's going to get out of the box, it needs to go through this straw. If we're going to make this act like a parallel circuit, then instead of attaching a second straw to the end of this, that it would have to go through both, instead, we could poke a new hole in the bag and let the air come out of a different straw instead. So now some of the air would be coming out through this straw, and some of it would be coming out through this straw. So here's two straws from the air demo. If I start with this straw connected to the bag, I push it down, it has some amount of resistance. It's harder to get the air to go through it, and as I push down and I push the air out of the bag, I can feel the resistance of that. Last time, what we talked about was connecting them in series. That would mean attaching a second straw to the end of this one. Now the air needs to go through both of them, and that takes more work. There's more obstacles in the way. That ends up increasing the resistance. That's series. Parallel, we're basically going to put the two straws, parallel to each other. We're poking a second hole in the bag. So now we have two straws, two different ways for the air current to escape. And if we push down, now that we've poked a second hole, even if that second hole has a resistor that's a higher resistance than the first one, we've still given the air a little more room, a little more options, and so it should make sense that the overall or equivalent resistance will be lower. So let's take a closer look and analyze this circuit in terms of Kirchhoff's current law and Kirchhoff's voltage law to try to figure out what that equivalent resistance will be based on the resistances of the two resistors that are hooked up. So I will draw our circuit a little bit bigger and give things some labels. positive and negative sign. So the battery has some voltage, V. That's the amount of energy it's giving each charge, basically. And then there's some amount of current, I, coming out of the battery. We'll say that the resistance of this resistor is R1, and this one is R2. Okay. So, Kirchhoff's current law says that we can't have the current appear or disappear. So for each point in the circuit, the total amount of current coming in equals the total amount of current coming out. So specifically, if we look at this point in the circuit, we've got some current coming in, and then we have this opportunity for the current to split up. Some of the current is going to go through this branch, through R1, so we'll call that current I1. And some of the current is going to go through this branch and then through R2. And we'll call that I2. So, the current law says that if we think about this point, the amount coming out, I1 plus I2, must equal the total amount of current coming in. Now, this is different from what we got in a series circuit where there was only one path, so the current was the same everywhere. Let's think about the voltage law. The voltage law says that any path from our battery plus to minus must use up all of the battery voltage. This basically relates to the conservation of energy. So that means that whether a charge goes through this branch or this branch, either way, it uses up all of the energy per charge that the battery was providing. So we could call this V1 and V2, but it's just going to be equal to the battery voltage. So V1 equals V2 equals the battery voltage. They're all just V. So instead of V1 or V2, because it's equal, I could just write V. Now let's think about Ohm's law. Ohm's law for the entire circuit, the same as it was before, is R equals V over I. But because we're talking about the entire circuit, which is the combined effect of these two resistors, I'll call this REQ for equivalent resistance. That equivalent resistance is going to be the voltage of the entire circuit, which we called V, divided by the current of the entire circuit, which we called I. For reasons that you'll see, let's rearrange this and solve for the current. We'll get I equals, so we multiply both sides by R, I divided by the R equivalent, and we should get I equals V over R EQ. This is just one of the alternate formats of Ohm's law. Now that we've thought about how Ohm's law applies to the whole circuit, we can also sort of zoom in and think about just one resistor at a time, and think about Ohm's law for this resistor. So it's going to be I equals V over R, but for just this resistor, the I is I1, the V is still the same as the voltage for the entire circuit, and the R is R1. And then same idea for this resistor, we'll get the equation I2 equals V over R2. So now we have an Ohm's law for the whole circuit, an Ohm's law for the first resistor, and an Ohm's law for the second resistor. Well, these three quantities are related to each other because of the current law. I1 plus I2 equals I. So I1 plus I2 equals I. Now instead of I1, I know that I1 is equal to V over R1. I2 is equal to V over R2. And the total current is equal to V over R EQ. Now I can just divide both sides by V. And I'll get the equation. I'm just going to switch the order as well. 1 over R EQ equals 1 over R1 plus 1 over R2. This is the equation for equivalent resistance in a parallel circuit. Unfortunately, this equation can be kind of tricky to solve. So let's do an example together, and then I will leave a different one for you guys to do yourself, but it'll be the same type of question. So this says find the total current if a 100 ohm and a 400 ohm resistor are connected in parallel to a 5-volt battery. I could draw the diagram if I wanted to. It would just be this diagram, and I could label 5 volts, 100 ohms, 400 ohms. Because I want to find the total current, that means I'm going to need to know the equivalent resistance first. So the first thing I'm going to do is find the equivalent resistance. And I'm going to use this equation, 1 over the equivalent resistance equals 1 over 100 ohms, that's going to be R1, and plus 1 over 400 ohms, that's R2. So I've got an equation, I've plugged in everything, and I want to find this REQ. You might think it's going to come out to be 500 ohms, but that would not make sense with our prediction. And it doesn't make sense with the logical thinking of more current is going to be able to get through because it has more pathways to go down. So you have to be pretty careful when you do these. 1 over 100 is 0.01. 1 over 400 is 0.0025. So that means I have 1 over REQ equals 0.0125. This is also not the answer for the equivalent resistance. Once you have this number, let's do a little bit of algebra to solve this. I want to find this variable that is on the bottom. So I'm going to multiply both sides by REQ. And I'm going to get 1 equals 0.0125 times REQ. Then I'm going to divide both sides by this number. To find that the equivalent resistance equals, let's try this division. I think it's going to be 80. Maybe not. Yeah. Equals 80 ohms. So my two resistors were 100 ohms and 400 ohms. My equivalent resistance when they're combined together in parallel is 80 ohms. Couple of tips here. First of all, from this point to this point is always the same process if you want to. When you get to 1 over REQ equals a number, you can just use this same logic and know that you're going to always do 1 divided by that number to find the actual equivalent resistance. So if you, in a different example, had 1 over REQ equals 0.02, you can just skip to equivalent resistance equals 1 over 0.02. You would do the same steps as we just did, but you don't have to do it every time. You'll get a little bit used to doing this process, and when you get to this point, you do 1 over whatever this number is. The other thing that's a good check is this number is usually, if the two numbers are fairly different, it's usually a little less than the smallest of the numbers. So our resistances were 100 and 400. Our answer was 80. That makes sense. If we got 800, we would know that that's wrong. If we got between the two of them, we would know that that's wrong. It shouldn't be 300 or 150. It's always going to be less than each of the individual resistors. And if they're fairly different numbers, then usually it's close to but less than the smallest of these resistor numbers. Okay. This isn't quite what the question was asking, though. The question was asking us to find the total current. So now we can use Ohm's law for the whole circuit. I equals V over R EQ. The voltage, or you could use this one, REQ equals V over I. You're plugging in the same things. This one's just already solved for I, so we might as well use this. The V is 5 volts. The equivalent resistance is 80 ohms. So this is going to be 0.0625, I think, amps. Let me double check that. 5 over 80. Yep. So this many amps, or we could write this as 62 milliamps. Okay. So when you do a second example, it's going to be the same process. You're going to have to do 1 over each of the resistances, add them up, do 1 over that number to get the equivalent resistance, and then plug it into Ohm's law for the entire circuit. All right, good luck.